In this video, we're going to talk about how fats make it to the skeletal muscle to be utilized, how they get from adipocytes all the way to the skeletal muscle. I'll use this simplified diagram to illustrate what's going on. So let me orient you with what we have. Over here in the bottom right, we have a muscle cell that wants to utilize fatty acids for energy. And up in the top left, we have adipocytes, where we store fatty acids for use later. The challenge that we're going to have is getting the triglycerides that are stored in the adipocytes down to the skeletal muscle to be utilized. That involves several hormones to get the fatty acids out of the adipocyte. It involves carriers in the circulatory system to get it to the muscle cell, and then things to take it up into the muscle cell. As you can imagine, it's kind of a slow process, and this contributes to the slow ATP resynthesis rate of fatty acids. So fats they don't mix well in water, right? Oil and water don't mix very well, and fats need to be transported in your circulatory system with something that handles water or blood a little bit better. And so typically your fats are going to be carried in a lipoprotein, like low density lipoprotein, like LDL, HDL. These are carriers for triglycerides and fatty acids. And so illustrated here, we have a bunch of triglycerides stuffed inside of a lipoprotein. I kind of imagine this as like a jelly donut stuffed with a bunch of fat instead of jelly. It carries it throughout the circulatory system. And you have two versions of an enzyme, lipoprotein lipase. One version that's on the adipocyte and the other version that's on the skeletal muscle cell, or on the capillary near the skeletal muscle cell, I should say. And they take the triglycerides out of the lipoprotein and get them into the skeletal muscle cell to be utilized, or into the adipocyte to be stored. Now, let's start with the version of LPL in the skeletal muscle. It's a little bit simpler here. So let's say that you need fatty acids in the skeletal muscle. One option is to just have the lipoprotein lipase enzyme on the skeletal muscle bring the fatty acids in. Now, this enzyme is going to be activated under a fight or flight response. So times of high epinephrine, norepinephrine, you'll see high lipoprotein lipase of the muscle. So you'll see a lot of take up of triglycerides into the muscle during that. Now notice that it's inhibited by insulin. So when you're in rest and digest mode, like after having eaten or relaxing and you have high levels of insulin, you're not going to be able to take up the triglycerides into the skeletal muscle very much because insulin inhibits that enzyme. So during exercise, when you have a sympathetic response, this will be upregulated a bit so that you can get triglycerides in that way. Now, let's say that you just had a big lunch and had a lot of fat in it, and you got fat floating around, and you're not exercising, so you're probably going to be in storage mode. So we'll now look at the version of lipoprotein lipase that is next to the adipocytes. So this version works a little bit differently. It still gets the triglycerides into the target cell, into the adipocyte, but it's sensitive, or its activity is sensitive to different things. The version on the adipocyte is sensitive to insulin. In the presence of insulin, this enzyme works harder. It's going to bring more triglycerides into the adipocyte. That's in contrast to the muscle version over here, which is inhibited by insulin. So after exercise or after eating a dinner, you're going to be signaling for storage of triglycerides in the adipocytes, not in the skeletal muscle. Now, it's also stimulated by high glucose, which is very similar to this rest and digest condition. Now, once you have the triglycerides in the adipocyte, these fat cells, it'll just hang out there until it's necessary. It's a storage depot. And you have these adipocytes all throughout the body, under the skin, in the belly, all over the place. And they're going to be hanging out there. until stimulated and broken down by a series of enzymes. And one of the key enzymes here is called hormone-sensitive lipase, HSL. And this enzyme is going to break down the triglyceride from the glycerol backbone. So this part that looks like an E, that's just this part here. That is like a 3-carbon backbone. And then, so you get the glycerol, and then you have the zigzags, which would be fatty acids. So it breaks it apart, the triglyceride, into glycerol and fatty acids. And the fatty acids, remember, they don't mix well in water or blood, and so they need to be carried. And they're going to be bound to usually a protein called albumin. This is just a protein that helps carry everything around, the fatty acids. This glycerol can then be utilized elsewhere, can be converted back into glucose and utilized that way as a source of energy. Now let's look at the activity of hormone-sensitive lipase. It's sensitive to hormones, as the name would suggest. And some of the most important hormones are going to be epinephrine and norepinephrine. So during times of high sympathetic activity, so intense exercise, you're going to have epinephrine, norepinephrine signaling to hormone-sensitive lipase, and you'll also have glucagon during high intensity activity or during times of hunger, signaling to hormone-sensitive lipase that will cause for the increased breakdown of fatty acids or of triglycerides and putting them into circulation to be utilized. So when you have high epinephrine, norepinephrine, that's going to signal for adipocytes to break down triglycerides and put them into the blood to be utilized. Now notice this is hormone-sensitive lipase. So this is an H here. And that becomes important because hormones go everywhere, right? A hormone isn't just localized to one area. Hormones get in the blood and circulate throughout the body. So adipocytes throughout the body that are exposed to epinephrine, norepinephrine, and glucagon will experience an upregulation of HSL activity. So sometimes we have this idea that if I have fat under my arms, if I do arm exercise, it's going to burn the fat there exclusively. Or if I have a beer belly and I do a bunch of crunches and sit-ups or buy an ab roller, I'm going to get rid of the fat and suddenly I'll be able to see my six-pack. It doesn't really work that way. This is a hormone-sensitive thing, right? So when you exercise, you have a sympathetic response. It's going to send hormones everywhere. And you'll have epinephrine, norepinephrine going to the fat. If you're doing crunches, you'll have epinephrine, norepinephrine going to the fat in your belly, the fat under your skin, the fat in your legs, just all over, okay? Not just specific to where you're exercising. And then all the fats throughout the body will be mobilized into the circulation. So you're going to burn a little bit of fat from everywhere, not just where you're exercising. Now, let's look at things that inhibit hormone-sensitive lipase, lactate and insulin. So when you're in a rest and digest scenario, like you would have high insulin, it makes sense that insulin would inhibit this, right? So insulin is signaling for the uptake of triglycerides into the adipocyte. So it also makes sense that it would inhibit hormone-sensitive lipase to keep them in there. Now, lactate is a really interesting one here. When we do high-intensity exercise, we actually reduce fatty acid oxidation. It takes a little longer to recycle ATP by oxidative phosphorylation of fats. And so we actually shift away from fats towards carbohydrates at high-intensity exercise. But the higher the intensity of the exercise, the more norepinephrine and epinephrine we see in the blood. So why wouldn't we see a lot of fatty acids in the blood during really intense exercise? Well, part of it is that during really intense exercise, we're going to see lactate accumulate in the blood, right? This muscle cell is going to go through glycolysis and produce lactate. And that lactate is going to get in the blood, and then it makes its way to The adipocyte, just like a hormone, in fact, you could consider it a hormone. The lactate's going to signal for decreasing HSL activity, and that contributes to decreased fatty acids appearing in the blood. So as you shift to more and more carbohydrate metabolism, higher intensity exercise, you produce lactate, and that inhibits this. So you'll see less fatty acids showing up in the blood at high intensity exercise. Another reason why we see less fatty acid in the blood at really high intensity exercise is that while epinephrine and norepinephrine signal to HSL, hormone sensitive lipase, they also cause vasoconstriction in the circulatory system, where it's going to decrease flow into the adipocyte. So you won't see a lot of blood flow going into the adipocyte. If blood isn't going toward the adipocyte, you can't really take fatty acids out of the adipocyte. So that's one of the reasons why we see less fatty acids appearing in the blood at really intense exercise, because we have less blood going to the fat cells. All right, so let's say during this moderate or heavy intensity exercise in this fat burning zone that you often hear about, we get the fatty acids into the blood. We've had epinephrine, norepinephrine, and glucagon signal for fatty acids getting into the blood. They're bound to the albumin and they're floating around, and they now have to make it to an active skeletal muscle. So in this diagram, it looks very simple, like it just goes directly to the skeletal muscle, but in reality, this would be pretty complicated, and you have to make sure that the blood is getting to the right place. And if you have poor artery function, then you might not get the blood going to the fatty acids going to the right place, and they might not be used. Let's assume that we have a good vascular function. We're getting the blood to the muscle cell. Once the free fatty acids make it to the capillaries near the muscle cell, you have a whole family of transporters. Here I just call it fatty acid transporters or translocase. It represents a whole family of these things. You can learn about them in more detail on your own if you want. But so all these different transporters are going to signal for the uptake of the fatty acids into the muscle cell. And once in the muscle cell, you can either store it as a triglyceride or you can utilize it. And if it's going to be utilized, like in the mitochondria, you have to go through activation, where you put a little phosphate onto here, you use some ATP to get the fatty acid prepared, and then you have to translocate it into the mitochondria. And then it'll undergo beta oxidation and be split. And then after beta oxidation, you got the Krebs cycle, electron transport chain that's going to be used to recycle ATP. So there are a couple of bottlenecks that you could have here. We've already seen that the activity of hormone-sensitive lipase regulates the availability of fatty acids. And then this process here of translocation is another spot where we see some regulation on how quickly fatty acid oxidation occurs. So make sure to study this and understand the general principle of how we're getting fats from the adipocytes to the skeletal muscle. Now you also have the fats, the triglycerides already in the skeletal muscle, kind of like glycogen is a stored form of glucose in the muscle. These triglycerides are also in there, and you can break them down and utilize them during the exercise as well. And it's up for debate exactly how much they contribute to energy utilization during an exercise. But with more advanced measurements and technologies, it's becoming apparent that we use these quite a bit during an exercise. They're not negligible, but we can use them. Interestingly, the fatty acids that we store in the muscle, we see high levels of fatty acids or triglycerides in the skeletal muscle in two populations. One would be a sedentary obese population, where you see a little bit more storage of fatty acids and triglycerides everywhere, including the skeletal muscle, and that has some complications and problems for the skeletal muscle. But we also see more fatty acids and triglycerides in the skeletal muscle of endurance athletes, which sometimes you call it like the fat paradox or the athlete fat paradox. The athletes store more triglycerides in the muscle and and they don't seem to have the negative effects of those triglycerides being in the muscle. And it might be because of the turnover rate. They don't stay in here for very long. They get utilized and broken down pretty quickly. Whereas in a sedentary obese situation where you might have these things staying around for longer and having oxidative stress and other things form, which impair the health of the muscle. In terms of supplementing fatty acids, there's really no reason to supplement fatty acids. We have plenty of fatty acids to fuel us through most of our exercises up to several days. I mean, if you're going on a trek across the United States, then you probably want to make sure that you're eating fats and carbs and proteins. But in terms of like normal single day activity, you probably have enough fatty acids stored throughout your body to fuel you through that. Really, the limitation point will be the glycogen. So let's talk about what happens to fatty acid during exercise at different intensities. I already alluded to this a little bit. Let's look at glucose first. So during low intensity exercise, like 25% of VO2 max, you don't see a lot of glucose getting into the blood. The blood glucose levels stay relatively constant. And this is probably because during low intensity exercise, you're going to be fueled primarily by fatty acids. And so you don't have as much sympathetic activity stimulating glucagon for glycogenolysis. But as you get up to like 65% VO2 max or 85% VO2 max, you see a lot of an increase in blood glucose. This is happening because you're signaling to the liver to break down glycogen and make glucose available for use. And then after the exercise, you see blood glucose levels go back towards normal after an hour or so. Fatty acids have a different story. So here we have fatty acids during 25% of exercise, 25% VO2 max for about 2 hours. And you can see the fatty acid levels are relatively constant during the exercise at that intensity and then bump up a little bit after. If you go up to 65% or 85% VO2 max, things get a little more interesting, where let's just go at 85%, you actually see a drop in the availability of fatty acids in the blood. There's less fat circulating in the blood during intense exercise. This is probably because of sympathetic activity reducing blood flow to the adipocytes, and also also lactate inhibiting hormone-sensitive lipase. These things are probably contributing to the decreased amount of fatty acids in the blood. But as soon as you stop the exercise, you see a rebound and an increase in fatty acid in the blood. So now you'll have decreased sympathetic activity, decreased lactate, and all these things result in greater fatty acid in the blood after the exercise. And you see the same general trend at 65% VO2 max. So 65%, you'll see at the start of exercise a slight dip, and then as the duration of the exercise goes on, you'll use more and more fatty acid or put more into the blood. That's really common. As exercise goes on, you tend to become more and more dependent on fatty acids. But then look again, as you hit the recovery, it shoots up and then it comes back down. So you'll see a lot of fat make it into the blood during recovery to be utilized for recovery of exercise. So this is a graph straight from your textbook showing what factors, whether it's glucose, glycogen, triglycerides, how much each one plays a role in fueling different exercise intensities. And the general rule of thumb is the more intense the exercise is, the more reliant you'll be on carbohydrates and less reliant you'll be on fats. And then the longer duration, the longer you go, the more fat you'll use. So we've already talked about this idea of spot reduction. You'll see it on late night infomercials, advertising like an ab belt that will electrically stimulate the abdominal muscles to do some contractions. And if they're exercising, or if you're electrically stimulating them, they're contracting, they're doing exercise, they're burning calories. But remember, everybody has abdominal muscles. You don't have the six-pack because you might have more fat adipocytes and fat tissue there over the abdominal muscles. And so in order to see the six-pack, you would have to reduce how much fat is there. And if you're just going by activating a little bit of muscle with an ab belt or doing crunches. You're strengthening the muscle, probably not a ton with the ab belt, but with crunches or like in a core workout, you're going to strengthen those ab muscles, but you're not going to send out a lot of epinephrine and norepinephrine for a long time. You're definitely not just going to send the epinephrine, norepinephrine to the fat right on the abs. It's going to go everywhere throughout the body. This idea of exercising a single muscle to reduce the fat around that muscle doesn't seem to pan out in physiology. So if you're trying to reduce how much fat you have over your six pack, the better bet than doing ab workout would be to do something that's going to have a large increase in epinephrine, norepinephrine, and a large and prolonged increase in VO2. And so you would see exercise where you have a lot of fat oxidation. So this would be somewhere in the moderate or heavy intensity domain where you're being fueled by a lot of fat, burning a lot of fat during the exercise. It's going to involve whole body exercise, probably like running, jogging, swimming, cycling, rowing, these kind of ideas where you have a really high caloric expenditure, and that's going to be signaling for fat oxidation and lipolysis throughout the whole body. Now, there are some studies that are showing that high intensity exercise, kind of like this, or even above 85% VO2 max, if you did something like 115% VO2 max, you'll see during that, you'll see a decrease, in fatty acid in the blood, and then you'll see a rebound. And we see that with fat oxidation as well. During really intense exercise, like high intensity interval training or sprint interval training, you don't see a lot of fatty acid oxidation during the exercise, but during the recovery, you do. And so if you're trying to target like losing fat, you want to do something that's going to have a high caloric expenditure, a whole body exercise. Treadmills often and workout guides often try to get you into this fat burning zone. And that's really trying to get you somewhere in this area where you're getting a lot of your fuel from fat. Now, there's more recent data suggesting that if you even get up to like 100% or 115% of your VO2 max, really high intensity, during the exercise, you don't burn a lot of fat, but during the recovery, you do. So when you think about exercise, you also have to think about the recovery. Okay, that is all I will show you for today. Study up, read in the textbook, and soon we'll talk about what determines whether we're using carbohydrates or fats during exercise and how we can measure that.